Okay, we're going to go over number 11 from the 2015 Geometry Common Core exam that was given last August. All right, so let's go ahead and read it. It says, Linda is designing a circular piece of stained glass with a diameter of 7 inches. She's going to sketch a square inside the circular region. To the nearest tenth of an inch, the largest possible length of a side of the square is, and then you have 4 choices. Now, a couple things I want you to write down. First of all, the largest square, so this note here, the largest square that can fit into a circle is the one that is inscribed in the circle. So I want you to write that down. Also, I'm going to draw, just so we remember what a diameter is, that would be the line that goes to the center point and touches 2 points on the circle. All right, so hopefully you wrote that down. Now I'm going to go over and I'm going to construct a square inscribed in a circle. This will be a little review, but this will help us to do this problem and understand it. All right, so I have my compass here. So if you remember, first thing you want to do is draw a circle. You also have to do or mark the center point. All right, now I'm going to draw a diameter like so. All right, the next thing I'm going to do is do the perpendicular bisector. So when you do that, you have to put your compass on the edge of the circle and draw an arc. Just make sure it goes more than halfway. It doesn't matter if it's here or here. So I'm going to draw an arc. And I'm going to keep my radius of the compass the same. Switch it over here. Don't change the radius or how much the compass is open. And make another arc. And I'm going to draw a line through the intersection. And I want it to hit both points of the circle. So you could just draw it all the way, but I'm just going to keep it here just to make it a little easier to look at. All right, so now I'm going to get rid of these arcs. And I'm going to just group this here just so I can... All right, so I already have the square, or no, I don't have the square yet. Next thing I need to do. I need to connect these points. Now, what you've done when you do this construction is you have split this circle into 4 equal sections, 1, 2, 3, and 4. So now if I connect these points here, here, like this, and like this. Now, I actually have a square. Okay, what I'm going to do is remove these 2 diameters from my circle with my square inscribed. And I'm going to group this together. And I'm just going to do that. Now I'm going to look at it just like this. So, you can see that we have a square. All right, so now, the next thing that we're going to do, let's not forget what our question was. It says, I'll go back here. It says to the nearest tenth of an inch, the largest possible length of a side of the square is what? Well, you know, you could have, inside of this circle, remember a square, all the sides are congruent. So we could have, we could have drawn a square like this inside a circle, but again, it's asking what's the largest square or the largest that the side length could be. So the largest possible square you're going to get on the inside of a circle is going to be the one inscribed, and that's why we constructed this. Now, we need to know how long would one of these sides be if the diameter, remember the diameter they actually said in the problem was 7 inches. So let's just remember that the diameter is equal to 7. All right, so think about that for a second. All right, so how are we going to figure out the length of one of these sides? All right, what you can do, I'm going to take away what I just drew there. I'm doing the wrong thing. I'm going to take away this diameter that I just drew. And see if I can make this happen. Okay. Now, what I'm going to do is draw a different diameter. I'm going to draw it like this. Okay, now, if you notice here, I've actually created 2 triangles. And both of these triangles have right angles. And we also know that this side, or the hypotenuse, is 7. So maybe you can figure it out from there. So try that. All right, the good thing about a square is that we know that this side is x and this side is x. We can label them x because we know that they are the same length. So you could use y, you could use x, it really doesn't matter. But the fact we have a right triangle means we can say x squared plus x squared is equal to 7 squared. So we'd end up with x squared plus x squared is 2x squared is equal to 7 squared. And 2x squared is equal to 49. Then we divide that by 2. We end up with x squared is equal to, you can keep this as 49 over 2. Or you could write it as 24.5. Either way, in both cases, though, you're going to have to take the square root. So that's going to be x is equal to the square root of 24.5, which, if this were a part 2 question, you said that the length was the square root of 24.5, you'd be okay. Unfortunately, this is a multiple choice question, and the square root of 24.5 is not there. Now, you should, based on your knowledge of numbers, you should know which one of these answers makes sense. Because remember, if we're looking at the square root of 24.5, we know that the square root of 16 is 4. We know that the square root of 25 is 5. And we know that this falls right in between. So it has to be in between 4 and 5, which leaves us with answer 2. Now, you have a calculator, so just go ahead and plug it in either way, and you get 4.93, I believe. 4.94, actually. And that rounds to 4.9. So that is your answer for number 11. Okay, looking at number 12. It says, in the diagram shown below, AC is tangent to circle O. So AC would be, right here, is tangent to circle O at A. That's right here. And to circle P at C. OP, segment OP intersects AC at B. Segment OA is equal to 4, AB is equal to 5, and PC is equal to 10, or is equal to 10. Okay, so I want you to write down these notes, which you have to know if you want to do this problem. So write these down. So if a line is tangent to a circle, then it is perpendicular to the radius drawn. And lines perpendicular to each other create right angles. So we can now say that we have 2 right angles. So take a second and write this down. Okay, hopefully you paused that and wrote down these notes. So based on the information in the problem, we have right angles here and here. That might help us. Also, Well, what are we looking for? We're looking for the length of BC. So let me erase this. What are we actually looking for? The length of BC. So we want this right here. So if you look here, we have two different triangles. And I want you to focus now on similar triangles. So hopefully you wrote this down, but I'll talk to you about it now. What is one way that you know two triangles are similar? Well, one of the ways you know is if two of their angle measures are equal or the same measure. If two of them are equal, then the third one is also equal. So all you have to do is know that two are equal. That means the third one is equal, and similar triangles always have equal angles. All right. Also, their corresponding sides have the same ratio. So you might be wondering, well, this doesn't say anything about similarity. I don't see similar anywhere in here. But if you look at these two triangles, I'm about to outline here and here. We know that these angles that I just marked, OBA, so angle OBA is the same or congruent. The measure of angle OBA is congruent or equal to the measure of angle PBC. And we know that because they are vertical angles. We also know, and we determined before, that angle A and angle C are both right angles. That means we have two angles congruent, and that means that these are similar triangles. So because of the fact they are similar triangles, we know that the corresponding sides have the same ratio. So we can actually set up a proportion. Now I want you to think about it. If this is the right angle and that's the right angle, then point A corresponds to point C, point O corresponds to point P, and B is fixed. So that just corresponds to itself. So just remember that. Think of it like if you're moving this thing and almost rotating it, all right? So we know what corresponds to what. So that means that the sides that correspond will be OA, which is 4. So we can do 4 over 10 is equal to 5 over BC. Because remember, if I were to fold this around, AB would land on BC. So that'd be 5 over X, because that's what we're looking for. So try and solve that. All right, hopefully you solved it, but let's go ahead and just do it. You can cross multiply. So you have 4x is equal to 50. Divide by 4, divide by 4, and you end up with x is equal to 12.5. All right, number 13 in the diagram below, which single transformation was used to map triangle A onto triangle B? So A is your pre-image and B is your image. All right, this is pretty, I'm not going to spend too much time on this. This looks pretty obvious. We just have a rotation here, all right, from A to B. So don't have any notes for you to write down. We just know that we know that this is what would happen if you have a rotation. All right, so this is pretty obvious. So hopefully you'll get this one right if it comes up on the test. Okay, here, just have a little note I want you to write down. When you're dealing with rotations and dilations, the corresponding angle measures will remain the same from the image, from the pre-image to the image. So let's read the question, though. I should have done that before I read the notes, but let's read the question. It says, in the diagram below, triangle DEF, so that's DEF, is the image of ABC after a clockwise rotation of 180 degrees and a dilation, where AB is equal to 3, BC is equal to 5.5, AC is equal to 4.5, DE is equal to 6, FD is equal to 9, and EF is equal to 11. What I want you to focus on is when you have triangles being the image of each other, or pre-image versus image, you can look at the lettering to see which sides correspond. Because in a figure like this, it might be confusing which ones correspond. But if I look at DE, that must correspond to AB, right? So when you took AB and you did the dilation, AB is actually going to come over here and correspond to this. And then EF corresponds to BC. So EF, so this is going to come and correspond to this. And the other side also. All right, so just remember that. And I might actually draw, since, so B is going to be where E is. So maybe I'll actually draw something. This is where B is. Like I'm actually going to maybe like rotate just so they're right on top of one another. So B would be there, C would be here, this is B, C, and A would be right on top of D. So now we have that. Again, what I'm doing is showing you, right? Showing you what would happen if I actually took this and went like this, right? Okay, so which relationship must always be true? And they all deal with angles if you look at the four answer choices. And let's see, let's look at number one. Is the measure of angle A over the measure of angle D equal to 1 over 2? Well, that's not going to be the case because we don't know that for sure, A and D. Well, first of all, they're corresponding angles. So if they're corresponding and you do a dilation or rotation, they're going to be the same. So it's not going to be a 1 to 2 ratio. It'll be a 1 to 1 because they're the same. So what about C to F? Well, C corresponds to F, right? So remember, if we look up here, C corresponds to F. So if they are similar, well, they are similar, and the angle would be the same. And here it shows C to F actually would be a 2 to 1 ratio. Well, that's not right. And let's see, what about number 3? Measure of angle C over the measure of angle, measure of angle A over the measure of angle C is equal to, so C over A is equal to F over D. No, that's not the right order. If it was A to C and then D to F, it'd be all right, but not that way. Last one, measure of angle B, which is here, over the measure of angle E, corresponding, is equal to the measure of angle C over the angle, or the measure of angle F. There we go. That's our right answer.